Okay, let's apply the subring and subfield test to two examples here. The first example we're going to look at is the collection of Gaussian integers. Gaussian integers are the sort of the complex numbers that have integral, real, and imaginary part. So that's what they are as a set. We can draw C, of course. So C looks like this, and here's sort of the real axis and the imaginary axis. And if we were to draw the Gaussian integers, let's draw them as maybe, I don't know, green. Then it's just all points that have that are on sort of the natural grid that we get, the natural integral grid inside of here. So these green points represent the Gaussian integers, and I feel like it needs to be even in each area. All right, and that just goes on forever. To infinity in all directions. This is sometimes also called the Gaussian lattice. Anyways, this is what it is. And so, for example, you have this point here, which is like 2 plus 1i. That's a Gaussian integer right there. So certainly not all complex numbers are Gaussian integers. Okay, so that's what this is as a set, and this is what it is visually. The claim is z adjoin I. This is how you pronounce it. So z sort of adjoin I, and we'll come back to adjoining things to sets later on in the course. The claim is this is a subring, but not a subfield of C. C, of course, is a field. All fields are rings, so we can apply the subring test, and we'll see that this actually is going to fail the subfield test. So proof, let's start with the subring. I'm going to start by showing z adjoin I is a subring. What is the multiplicative identity in C? Well, the multiplicative identity is 1 plus 0i. Does it have integral, real, and imaginary parts? Certainly. All right, so we have 1. Fantastic. Suppose you have two Gaussian integers. So a1 plus b1i and a2 plus b2i are Gaussian integers. That is, the coefficients, the real and imaginary parts here, are integers. Then, what do we have to do for the subring test? We have to look at their difference. So a1 plus b2i a1 plus b1i minus a2 plus b2i, that's just going to be the difference of the real and imaginary parts. And when we compute this difference, a1 and a2 are integers, so their difference is still an integer, and b1 and b2 are integers, so their difference is still an integer. So this is still a Gaussian integer. So it's closed under subtraction. Okay, and now we have to check closed under multiplication. Let's keep the a1, b1, a2, b2 from before, and let's just look at the product now. You're going to be writing out lots of products in this class, which, it is what it is. So again, a1, b1, a2, b2 are as before. They're all integers. If we compute this product, we're going to get this expression that we've seen a lot. Product of the real parts minus product of the imaginary parts plus the cross terms times I. Now, that's certainly still an integer because it's a product and difference of integers. This is a product and sum of integers, so that's still an integer. So this whole thing is still a Gaussian integer. So what do we get? We get closed under multiplication. So these are the 3 checks we needed for the subring test. So what do we conclude? We can conclude that the Gaussian integers are a subring. That was part of the example. The other part is to show that it's not a subfield. So let's do that now. Let's notice that 2 is in Z adjoin I, and 2 inverse, the multiplicative inverse, is not in Z adjoin I, because the multiplicative inverse of 2 is 1/2. So it can't possibly be a field because it fails to have multiplicative inverses of non-zero elements. Now, we can actually visualize this. So let's go back up to our picture for the last thing we'll do for this example. Let me get rid of that red. So where is 2? This is 2. Oops. I'm going to mark it as 2. That was a green dot as well. Where is 1/2? I'm going to keep this as a green dot, actually. Where is 1/2? 1/2 is here. 1/2 is not a green dot. So you can see visually that sort of dividing causes us to leave the Gaussian integers if we were to represent it as this lattice.